Okay, I recorded this lecture because we didn't have class today, and so this kind of catch you all up, and that way we can proceed on schedule. And so I just want to talk about the rest of Chapter 3, and so Chapter 3 covers variation. All right, and so variation is spread, and now when we think of spread, I want you to think of how consistent is my data. So if I had data numbers ranging from 2 to 100, that's pretty spread out. But if I had data numbers ranging from 40 to 50, that's not very spread out. And less spread means more consistent. And typically in industry, more consistency is good. And so we want to think of that. If I have a product and it's very consistent, then I know what I'm buying, and people like that. All right. So we'll talk about variation, and more specifically, we'll hit the idea of standard deviations to do that. Now, one way to measure spread is range. Range is just the high minus the low. That's pretty boring. So in this case, it looks like a high of 47, a low of 37, and so the range is 10. And in this case, these are in thousands of dollars, so the range is 10,000. So that's pretty basic, and that's one idea of spread, right? I think everybody understands that. Now, the next concept, I really want to break this down probably a lot more thoroughly than maybe is needed, but I think it helps you to understand what is going on in this formula, all right? And so the next thing we want to talk about is what we call a deviation. Now, a deviation is just, to deviate is to move away from or to change. So how far are we away from the mean? All right, and so deviation is just your value minus the mean. So here, your value x minus the mean. So if it's population, it's the mu. If it's a sample, it's x bar. Okay. So for example, on the next slide here, here's some deviations, right? And this is that same salary data. I calculated the mean. And the mean's 41.5, and so there's your deviations. Now notice some of the deviations are negative, right? Well, why is that? Well, because all of those values are below the mean. So a negative implies I have a data value below the mean, and then the value itself tells you how much below the mean it is. And if it's positive, then it's a data value above the mean. So it tells you how far away you're deviating from the center, if you will. Now, notice something interesting here. So I got this idea of spread, right? So here's the mean, if you will. And so I have maybe data here, one's here, one's here, one's here, right? And then one's here, one here, one here, right? If you want to think about it. And now it might be kind of nice to say, okay, on average, how far is the data spread out around that mean? Well, how do you find an average? Well, you add everything up, divide by how many. But the problem is, when you add up all these deviations, you get 0. And it turns out, we're not going to show this or prove this to you, but it is possible. Every time you add up all the deviations, you always get 0. So if I was to add them all up and divide by how many, we'll add them all up, get 0, divide by how many, I get 0. So if I wanted to know an average deviation, it would always be 0. Okay, so that's not helpful. But gosh darn it, if I had an average deviation or some sort of concept like that, I think that would be pretty powerful. That would say, roughly this is on average how spread out it is. Okay, so we need to fix this. We need to get around it. All right. And so a couple ways to do this. You could say real simply, well, just ignore all the negatives and then you'd be good to go. Problem is we can't, that's not math. That's just, talking. So we got to do this in a formula way, a math way. One way to get rid of the negatives is an absolute value. We don't want to do that though, because absolute values are problematic when you get into calculus and you kind of take things up a step further in statistics using calculus. And so we want whatever we do to behave well with calculus. So absolute values off the table. So the other idea is, well, what if we square it? Because if I square a number, that'll get rid of the negatives. The only problem is, if I square a number, I've also changed the number, right? So, for example, negative 1/2 squared, right? 0.5, which is the same as negative 1/2, right? If you square that, that is a positive 1/4, right? So I've made it positive, but now the value's changed. So the idea basically is this. We're going to square everything. We'll add it all up, divide by how many, and then at the end we'll square root it to kind of get back to where we were. So that's kind of the idea if you want to think about it. And then that sort of essentially gives us an average deviation. And so when you do this formula, some new symbols by the way. So let's see here. This symbol, whoops, no, wrong buttons. This symbol here is sigma, so that's lowercase sigma. So sigma squared is what we call the population variance. And the formula says, hey, we're going to add everything up, and then we will divide by, we'll take the deviations, we'll square them, then we'll add all those up. Which, by the way, some books shortcut that or label that as SS sub x, in other words, the sum of the squares for the variable x. And if it's a population, we'll divide by capital N. All right. Now, if you take the square root of that, you get what's called standard deviation. And now if you take the square root of sigma squared, the square root and the square cancel, and then we just get sigma. And so like I said, we squared everything in here, but then to undo it, we will square root. And that kind of gets us back to where we started. So standard deviation is essentially like having an average deviation. So on average, how spread out around the mean am I? All right, so that's if it's a population. Those are your symbols. Now, if it's a sample, sample variance is S squared. And notice you don't divide by n, you divide by n minus 1 for a sample. And basically the reason is because it's a sample, it's not quite as accurate. And so to correct some of the inaccuracy, you divide by n minus 1 is essentially the idea. We could go into that a lot more depth, but that's not our focus, so we aren't going to do that. But if you want, you can come and talk to me about it, and we can go into that a little further, but just trust me, it works. All right. And then now if I take the square root of that, again, because we squared everything, and then we'll take the square root to undo all those squares. And that gets me back. And again, this would give me essentially an average deviation. All right, but we call it a standard deviation, so S is the symbol for that. So again, if we're keeping tabs on our symbols, we got a couple new symbols then. So for a population, we have sigma squared there. If it's a sample, it's S squared. Sigma is standard deviation. S is standard deviation of sample. And remember, these are all statistics, right? And then the column left of that is all parameters, right? And so again, if we can understand these symbols, we can understand our formulas better, we can put the right numbers in the right spots, and everything's good. All right, now these are basically the steps if you need to find the standard deviation by hand. So you can review those. But if you ever have to do this, the best way, honestly, is to make a table. If you have to compute this by hand, there's just no other way around this. So you can see in this column, I did all the deviations, and then we squared them to get everything in this column, and then we added all those up to get the sum of the squares, which is the same thing as this top number up here, right? So there it is. I got that top number up there. In this case, it was a sample size 10. So it's 10 minus 1 on the bottom. And so your variance is 9.833. Your standard deviation is 3.136. Which I think, if we go back over to this column, right? Look at all those numbers: a half, 3.5, 2.5, 3.5, 5.5, a half, 2.5, a half, 4.5, a half. On average, I mean, kind of 3.13 is sort of an average of all those. So, yeah, on average, I'm spread out roughly 3.13 away from the mean. Okay. So the smaller the standard deviation, the less spread. Okay. Now, of course, don't do this by hand. It's modern times. Let's enjoy the fruits of that. So if you type this in a column in StatCrunch, then you can just click on the buttons as shown on this slide. I also have some videos where I show how to do this in StatCrunch as well. And you can watch those videos. But StatCrunch will just spit this right out for you. So there you go. So it's real nice and easy. And so just do that when you're doing problems. Use StatCrunch. Okay. Now, the next thing is the range rule of thumb. This is pretty powerful and helpful. So first of all, if you don't know the standard deviation, it's approximately the range divided by 4. And this is the idea. So think of this as being the middle, right? And so the mean is 0 away from the mean, right? Because it's itself. Now the 1, the 2, and the 3, and the -1, the -2, and the 3 are a standard deviation. So this is 1 standard deviation. This is 2 standard deviations. Here's 1 standard deviation, 2 standard deviations. And so the idea is, roughly speaking, the range, which is the high minus the low, is 4 standard deviations wide. In other words, almost everything fits between here and here, or should. Okay? And so that's why we use this kind of scale idea down here. So if you're within 2 standard deviations, then you are considered an ordinary value. If you're outside of that, that's considered an unusual value. And so if you want to know exactly, hey, where are these 2 boundaries, if you will, then you can crank out these 2 little formulas, and that'll tell you exactly where everything's at, or where these boundaries are, and therefore how can you properly determine what is usual and unusual. And of course, if you're out here and you're unusual, then that means you're an outlier. Okay, so let's see this in action. So let's go back to that same data. There is your, let's see here, your mean. Yeah, that's what it is. So your mean of 41.5 and 3.136, I think, was our S. So X bar plus 2 times 3.136, and I guess X bar in this case is 41.5. And we'll do the same thing. And so what do we get? So I get 47.772 and 35.228. And so in part B, would a starting salary of $48,000 be unusual? Yeah, it falls outside those boundaries. So yeah, that would be unusual because it is above this top boundary. So yes. Now C says use the exact standard deviation of S to find the boundaries. Oh, that's actually what I did here. And so let's see here. I can cheat and do this. Haha. Alright, up here, I guess I failed to realize, approximate, which is that range rule of thumb idea. So S is approximately the range divided by 4. And if you remember, our range was 10. And so 10 divided by 4 is 2.5. So there we go. So if I did that, that would give me 41.5 plus 2 times 2.5 would be 46.5. And if I do the same thing, 41.5 but minus 2 times 2.5, 36.5. So ordinary values would be between those two numbers. So actually, my answer to part B is still the same. And no, down here, does this change your answer? No, it doesn't. So whether I use that approximate or I use the actual standard deviation, I ended up kind of getting the same thing. Now obviously you can see they're a shade different in terms of where those boundaries are, but they are pretty darn close. Okay? Alright, so another thing is this idea of what we call the empirical rule. And so if you have data that's symmetric or close to symmetric, then it kind of follows this rule. In other words, this kind of is roughly how spread out everything is. And it's based on standard deviations. So about 68% of your data is within one standard deviation. You go out to 2 standard deviations, it's 95%. Okay, which is exactly why if you're outside of 2 standard deviations, that's kind of an unusual value, because that's only 5% of the data then. Only 5% of the data is outside 2 standard deviations, which if I told you something happened less than 5% of the time, you'd say, yeah, that's kind of rare. Or in other words, unusual. Okay? And actually, if you go out 3 standard deviations, that's pretty much everything, 99.7% of the data. So here it is in a visual form, and you can see those standard deviations. Every time you take a step out, you get more and more data. All right, and again, this is a normal distribution or a symmetric distribution. The idea being, is if I had a histogram, right, that was symmetric, right? If I had all these bars, and then I kind of traced out the shape of that histogram, it give me this curve, right? And we call that a distribution. So that's kind of what we're thinking about here. So if it behaves in this way, or roughly in a symmetric way, then we know the data is spread out in roughly in this manner. Okay, and so these are really, really good estimates. And the more and more symmetric you are, the more and more exact these estimates are. All right. Some other ideas to wrap your head around, though. And again, these are all just estimators, ways to wrap your head around how spread out the data is. Chebyshev is how you pronounce that. So Chebyshev's theorem says the proportion of the data within a certain amount is at least this formula here. So if k is 2, you plug in 2, so you get 1 minus 1 over 2 squared, right? So 1 minus 1 over 4, that's 3/4, or in other words, 75%. So in other words, at least 75% of the data lies within 2 standard deviations. So up here, if you're 2 standard deviations, we said 95%. So that's what we think it is, or very close approximation if it's symmetric. But we also can note, hey, we're really confident though it's at least 75%. If it's not 95 exactly, it's very, very safe to say it's at least 75. And then with Chebyshev's formula, you plug in 3, you get 89%. So again, going back a slide, if we go 3, we said, hey, we think it's 99.7% of all data, because it's almost everything, right? But Chevy Chef says, well, I don't know exactly what it is, but it's at least 89%. So again, it's just another way to get an estimator to wrap your head around what's going on. So let's see that in action here with this example. So let's say you have IQ scores. IQ scores have a mean of 100, a standard deviation of 15. So what's the empirical rules say about 2 standard deviations? Well, 2 standard deviations would be 30, because 1 standard deviation is 15. So subtract 2 standard deviations from the mean, add 2 standard deviations in the mean. That's 70 to 130. And the empirical rule says 95% of IQ scores then, scores, there we go, are between 70 and 30. And what does Chevy Chef's rule say about it? Well, at least, from that last slide, 75% of IQ scores are between 70 and 30. 70 and 130. Sorry, 130. There we go. So again, these are just mechanisms to get the idea of spread. What does that mean, and what does it tell you? Okay. Another way to compare things and talk about spread is this thing called the coefficient of variation. And so this is how you can take 2 data sets that aren't quite the same and then talk about what's more spread. Because if they don't have the exact same center, it's not fair to compare their standard deviations, right? Because if I'm talking about values that are centered around 5, a standard deviation of 10 is kind of a big deal, right? But if I'm talking about values that are centered around 1,000 and there's a standard deviation of 10, moving 10 up and down from 1,000, not so much a big deal, right? And so when you have 2 sets of data that are not centered on the same thing, you can't really compare their S's to each other. So this is one way to do that, though, and the coefficient of variation allows you to calculate, and then you compare the coefficient of variations, and then you can say, okay, this one's more spread. Okay? All right, last is what we call the 5-number summary and box plots. Okay? And these are our last tools to talk about how do we calculate spread and show that. All right. So before we get into that, though, let's talk z-score real quick, or the standard score. 2 formulas. Again, it's the exact same formula. It's just here it's a sample, so x bar. Here it's a population, so mu. Here it's a sample, it's S. So here it's a sample, it's sigma. But both of these are the mean, and both of these are the standard deviation. It's just the proper symbol for what we're dealing with. All right. So z-score, it's a way to standardize things. So first of all, what's this up here? That's a deviation. So how far from the mean are you? And then you divide by the standard deviation, which standardizes it. All right. And this allows us to compare apples to apples, if you will. All right. And the nice thing is, if we calculate a z-score, we can think about this exact same scale. But instead of calculating the 2 boundaries, we just calculate the z-score and then say, oh, where do you land on this scale? All right. As an example, author of a textbook measured their pulse rate to 48 beats per minute. And so is that pulse rate unusual? If the male pulse rate has an average of 67.3 beats per minute with a standard deviation of 10.3. So just plug all the numbers in. So the data value X is 48, and the mean is 67.3, standard deviation is 10.3. Crank it out, you get negative 1.87. By the way, if you're going to try to do this all in your calculator in one chunk, make sure you put parentheses around the top. Yeah, and so remember, normal, negative 2 to 2. Where are we at? We're over here at negative 1.87. So yeah, that's normal. Okay, that didn't fall outside of those boundaries, and so we would consider that an ordinary or normal value. Seems kind of low, but actually, according to this, it's not. So z-score is just another way to do this and to gauge whether something is usual, unusual, and just get an idea of how spread out or far away from the mean it is. Okay. Percentiles is another measure of spread. And so percentiles, if you've taken standardized test, if I say you scored in the 87th percentile, that means you scored better than 87% of everybody else. So in other words, 87% scored less than you did. So it's just taking the number less than a certain value and then figuring out what percent less than that value there is. Okay, so that's what a percentile is. All right, so example, here's some Chips Ahoy cookies, and here's the number of chocolate chips in them. So man, that's a lot. So find the percentile for a cookie with 23 chips. So I need to find everything that has less than, so not equal to, but less than 23 chips. So let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 out of how many? Looks like it's 10 out of 40. And so that's 1/4 or 0.25, and so multiply by 100 to turn it into a percent, and so 25% or 25th percentile. All right, so that's all there is there. That's just again another way of gauging spread and where is a data value. All right, last is quartiles. Quartiles are really easy. And we combine quartiles with the high and the low, or the maximum and the minimum, and that gives us what's called the 5-number summary. Basically, all you need to do is you find the median that splits the data into a lower half and an upper half, and then find the median of those two halves, and those give you your 3 quartiles. And so notice here, the median is the 2nd quartile. All right. So here's an example. I'm using this power plant data, and so if I order the data, first of all, find the median. Here's my median, and so now I have a lower half and an upper half. And now, what's the median of the lower half? 10. What's the median of the upper half? 31. You do not include 18, by the way, in the lower or upper half. Okay, it's in the middle. And so there we go. And then if I add on to that a low and my high, that gives me 5 numbers, and we call that the 5-number summary. All right. And then with those quartiles, here's your Q1 and Q3, right? 10 and 31 in this case. You can calculate these values, and then these values are also used to kind of gauge spread. Now, if you're working with quartiles, you can use quartiles to also gauge outliers. All right, so if you take Q1 minus 1.5 times the interquartile range, which again, the IQR, just on the last slide, but remember that was Q3 minus Q1. And then you take Q3 plus 1.5 times the interquartile range. If you fall outside those boundaries, that would also be considered an outlier. So the question is, some of you might be saying, well, wait a minute, what do I use? Do I use standard deviation and twice the standard deviation, or do I use quartiles and this 1.5 thing? Well, you can use either, but it's about what do you have. Most of the time, we're going to work with standard deviation. So if we're working with standard deviation, we should use the 2 times the standard deviation idea. All right. But if I'm working with quartiles, then you would use this rule. Okay. So if I go back, what are my boundaries for my quartiles? My lower boundary would be quartile 1 minus 1.5 times the interquartile range. What is my interquartile range? In this case, Q3 minus Q1. 31 minus 10, so that's 21, and so that's what I'll put in here. And it's Q3 31 plus 1.5 times the interquartile range. So if I calculate those quick, $62.5 for the top, and of course this doesn't make much sense, but that's fine because the data is skewed, so that's why this isn't making as much sense. But the bottom one is negative 21.5. I don't even have any negatives, but that's fine. So what would we say if we use the range rule of thumb, which the mean, by the way, is 24.5 and 26.7? Well, that would be what? That would be 24.5 plus 2 times 26.7, and actually, let's move this over here because that's the upper one, and 24.5 minus 2 times 6.7. So if I was to use I typed 6.7, it's 26.7. As I say, these numbers did not look right. So minus 28.9 and 77.9. So you see, if we use the quartiles, we get those numbers in the middle. If I use the range rule of thumb and standard deviation, I get those numbers. They aren't exactly the same, but they're both kind of in the ballparks with each other, right? Now, regardless, if I look at this data set, whether I use quartiles or range rule of thumb, both of them say that this 104 value is an outlier. Okay, so it doesn't matter which version I use, they both say that. Yeah, and there are no other outliers. Everything else is between those values, so in each case. So there you go. Alright, so one more graph, that's the box plot. So if it's categorical, we can do a bar graph. If it's quantitative, then we can do all these graphs, and the additional graph we're going to throw in the mix here is a box plot. And so box plot, or sometimes we call it a box and whiskers plot, is we use that 5-number summary where we have the low, the high, and those quartiles. So the quartiles make a box in the middle, and then you draw a whisker out to the low and the high. That's why we sometimes call it a box and whiskers plot. All right. So if we go with the with this data from before, remember, here's your low, here's your high, those are your quartiles. And so if we draw this out, I get a box plot like this. Now, what's the advantage of a box plot? When you have a box plot, you can see that the data is really spread out. Okay, so the fact that this whisker is extremely long compared to the other one tells you the data is skewed, and that it is skewed to the right. Okay, And if I go to this slide, then I can definitely kind of see how everything matches up. So the box part is representing this chunk of the data, right? And then here is like the two whiskers, right? So that's essentially what's happening. All right, and it's another way of gauging and showing spread. Now, when you stack these up with each other, you get these two graphs like this. And so it is the box plot up top shows you, hey, this definitely is skewed right, spread to the right. The histogram down below also shows that, but histogram down below also shows where there's kind of a clumping here of data, so we get a little bit more out of the histogram. And so if you do a frequency table, a box plot and a histogram, that's kind of like the holy trinity of descriptive statistics, at least visually speaking. So those three things visually tell you a lot if you have quantitative data, and instantly you can get a real good sense of what's happening with your data with those three graphs. So that's what we typically do and we typically aim for. And you can do these all in StatCrunch. So again, put the data in a column, go to graph, and then you can pick all these graphs underneath there. StatCrunch will spit them out. I encourage you to do that. I also have videos on how to do these as well in Blackboard, so check out those videos. So, putting it all together, we want to know the context of the data, where the data is coming from. Hey, are we using good sampling methods? And then we can talk about measures of center, measures of spread or variation. We can make those charts to look at the distribution, in other words, the shape. That can also tell us skewness and therefore outliers. And then, of course, one thing to always consider is, do things change over time? Because just because something's true now doesn't mean it's always true. And then, hey, at the end of the day, can we come to any conclusions or practical implications? All right. So, whenever you have data, these are the kinds of things we want to look at when we're just trying to break it down and describe what's going on. And then we're going to learn that inferencing and all that in the later chapters, which is the big decision-making kind of stuff.